Welcome to the University of Maryland, Baltimore County. I'm Professor Erle Ellis of the Department of Geography and Environmental Systems here at UMBC. And today we're talking to Professor Wallace McMillan, who's a physicist who specializes in atmospheric physics and the study of air pollution.
Thanks, Earl. Glad to be here.
So to start with, I guess the best thing to do is to find out how you got involved in the business of looking at air pollution and trace gases from space.
Well, I started out as a kid wanting to be an astronaut. So my father took me to see 2001 when it opened in '68, and I haven't been the same since. I guess the first thing I really observed as a kid was that clouds were moving in different directions and different directions in the wind on the surface. And I asked my father, and he said, no, everything moves in the same direction. I said, that's not what I see. And so it was kind of the beginning of, I guess, me starting as a scientist and starting to look at things.
Interesting. So Space Odyssey, that's actually something I can identify with as well. I think a lot
kind
of
of dates
scientists.
us too.
Yeah, it does. So you've been at this for quite some time.
Been at it for a while. Didn't get to be an astronaut, but the next best thing is working with space data, satellite data. So as a graduate student, I guess about halfway through my first year at Johns Hopkins, Voyager 2 flew by the planet Uranus. My advisor was a member of the science team for the ultraviolet spectrometer on Voyager 2. And within six months of starting graduate school, I was starting to look at data that was hot off the press, looking at a planet that we really hadn't seen much of before. And it was fortunately far enough away that we could make models with a few knobs to tune to try to figure out what was happening, and there wasn't a whole lot of data to tell us one way or the other all the details.
So it was really the first look at a planet that really hadn't been seen before with any detail.
Yeah, it was, and it was very exciting. Uranus, for many people, is kind of a boring planet because it's kind of a pale blue ball with not a whole lot of features. So we really had to look in a lot more detail. We can't just look at the pretty clouds that we often see from Jupiter and Saturn. We had to look more in terms of the scientific data, looking at the spectra, both in the infrared and the ultraviolet.
So what does that really tell you about the planet when you start looking at the spectra of light coming from the planet?
It tells us the makeup of the planet. Just as any element has a characteristic spectrum, a characteristic fingerprint, so to speak, due to quantum mechanics, every atom molecule has characteristic spectra. So looking in different parts of the spectrum, ultraviolet, visible, and infrared, we can determine what the planet's made out of. And then with the different instruments, we can begin to develop vertical profiles of information. So we have an idea of what the composition is as a function of height in the planet.
So really how the chemistry of the atmosphere of these planets is functioning.
Right.
And the dynamics and this sort of thing.
It's a combination of both the chemistry and the dynamics. And so I started off looking at Uranus, spent a number of years as a graduate student. And then many people, including one of my brothers, had said, well, that's all fine esoteric stuff, but what does it do for humans?
Right.
And so since then, my work has moved progressively closer. I spent a couple of years at Goddard Space Flight Center working with the Mars Observer spacecraft, and then came to UMBC in '94, started to work with the Atmospheric Infrared Sounder, which is one of NASA's big instruments on the Aqua platform.
Okay, so tell me a little bit more about, first of all, the Aqua platform and what that means for Earth science and Earth observation, and then maybe a little more about your particular role in looking at the planet from
Well,
the
Aqua was originally, it was called PM because it was in an afternoon orbit. They gave it a better name once it was launched to focus more on the science that it was doing, which was, in terms Aqua, water, was really to focus on the water cycle. So there's a microwave instrument that looks at ice and surface parameters, and then there's AIRS, the Atmospheric Infrared Sounder, which primary job was to do temperature and water vapor profiling in the atmosphere and to look at some of the cloud information. And so really the prime driver for AIRS was to improve our capability for forecasting weather.
Okay.
And then longer term, the original plan from NASA was to fly a similar instrument every 5 years for at least 15 years to begin to look at climate.
So you started off more or less with weather.
Started off with weather
stuff.
That's kind of what pays the bills generally.
Okay.
And then in the process, because we have a good instrument and we see a lot of the infrared spectrum, we see not only water vapor, but trace gases. We see carbon monoxide, ozone, methane, and even carbon dioxide, which is getting carbon dioxide is a lot tougher to get to the scientific accuracy and precision that we need. Some of the other gases have been a little bit easier. So my primary job, really for the last 15 years, has been working with AIRS to improve the carbon monoxide product.
Okay, so you started off with this platform that was designed to look at the dynamics of the atmosphere relating to weather,
right,
and then started getting more into the climate aspects, and then you started looking at the trace gases from the point of view of climate change, perhaps, with the concentrations of some of these
right,
gases?
part of it is from the standpoint of climate change. Carbon monoxide is a principal byproduct of combustion. So anytime you burn virtually anything, especially anything with carbon in it, you're going to produce some carbon monoxide. The more efficient the burning, the higher the temperature, the more carbon dioxide you get. So being able to measure the two of those would be very key, because that tells you something about how complete the combustion is, how efficient things are. Carbon dioxide, as most people know, is a primary greenhouse gas next to water vapor. So being able to measure globally the distribution of carbon dioxide is really a key importance. And it's one of the things that actually there's a scientific meeting going on third week of December this year. There will be a major press release from some of the members of the AIR science team. And the other thing I really should focus is the work that I do is a small portion, work with a huge team of people all across the United States and really internationally to work with the data. And as to coin, other people have used the phrase, we stand on the shoulders of the giants that went before us. The work that I do is literally at the tail end of the processing of all the AIRS data. And we really require the high precision temperature and water vapor measurements that are done before we get to the trace gases.
So you're involved in a really large program to look at the dynamics of the atmosphere of the entire planet, and your particular focus has been on carbon monoxide, and I guess that involves combustion and fire. I think that's
right. It involves combustion and fire. The two main sources. The easiest thing we see are big fires wherever they're occurring on the planet. The second thing, which depending on where it's occurring, is either easy or hard to see, is man-made pollution, such as the United States. The Northern Hemisphere, there are a lot more people. There's a lot more carbon monoxide in general. So it's harder to pick out the major cities in the United States because the overall level, there's more carbon monoxide.
So you can see a city from space just by its carbon monoxide?
We can see some cities. Mexico City is one of the ones that we can see on a regular basis because there's a lot of people in a small area, it's at high altitude, and there are no sources around it. So Mexico City and the major petrochemical facilities to the north and east show up routinely on, not necessarily every day, depends on whether the satellite actually sees it every day. Tehran is another city that shows up as a prominent spot, again because there's a lot of people in a concentrated area and there's very few sources around it.
Very few fires or
other things.
Carbon dioxide. Oh, that's interesting.
The northeast plain of China, a region that you're very familiar with from your research, is a very heavily populated region, is one of the larger human influence regions that we see on a weekly, monthly kind of basis. There's almost always a lot of carbon monoxide there and downwind. Downwind of the United States, downwind of Europe, you can see plumes of carbon monoxide. Since we have a view nearly every day, sometimes twice a day, we can look at the dynamics. We actually see what we're moving towards from NASA is being able to forecast chemical weather, very much like we do temperature and water vapor for whether it's going to rain or whether it's going to be cloudy.
So it's a bad carbon monoxide day, it can tell us.
That's one of the things we're moving towards, being able to ingest the satellite data in a near real time to the forecast models for forecasting air quality.
So is carbon monoxide a really serious part of air quality in, say, a regular city? It sounds like it is. Is that really important?
In some places it can be. Fortunately, the studies that have been done before really we were making satellite measurements in the late 90s of carbon monoxide showed that carbon monoxide was increasing globally, especially in the Northern Hemisphere.
Carbon monoxide is increasing?
Carbon monoxide was increasing.
That's interesting. Now, carbon monoxide doesn't last very long in the atmosphere. Am I correct about that?
It has a lifetime of a few months. And so the primary source was humans. In the 90s and throughout the 80s and into the 90s, we put emissions controls on automobiles in the United States and Europe, and we actually saw the carbon monoxide levels flatten and then actually decrease.
This was seen from space, or was this more seen
This was seen from ground-based measurements.
Okay.
What we've seen from space, the satellite era, there's another instrument, measurement of pollution in the troposphere. It's a Canadian-built NASA flown instrument on the Terra platform, also measures carbon monoxide, launched in 1999. Between MOPIT and AIRS, we've seen the carbon monoxide levels overall in the Earth's atmosphere are relatively constant. There really haven't been a big increase, even from China. There hasn't been a significant increase in carbon monoxide. At the same time, our fossil fuel consumption is rapidly increasing. And what that tells us is that we're getting much more efficient in our combustion processes.
Really? You can see that from space?
You can see that from space, which is a good thing to be more efficient. The bad news is there's less carbon monoxide, there's more carbon dioxide.
I see.
And we don't have as long of a record of those measurements, but the measurements from AIRS, colleague Moose Shaheen, Larrabee Stroh, and Chris Barnett, each working on the carbon monoxide, show that over the lifetime, since AIRS has been in orbit since May of 2002, the global amount of carbon dioxide is increasing. And the work that's going on now is to use those satellite measurements to essentially invert them to try to figure out where are the sources and where are the sinks. We know where some of the sources are, but we don't know where all the sinks are.
So what is, now the idea of source and sink, I assume this is the idea that some stuff is coming from somewhere and that's a source, and stuff is going somewhere and that's a sink.
Right.
So what is a sink for carbon monoxide? What's an example of one?
Well, for carbon monoxide, the primary sink is oxidation with the OH radical.
And this is something that occurs on the ground, or how does this occur?
It occurs naturally in the atmosphere. I think roughly 85% of carbon monoxide is taken up by OH and goes to carbon dioxide.
So this is a natural chemical reaction in the atmosphere.
It's a natural chemical reaction in the atmosphere where carbon monoxide, there are two ways carbon monoxide is dangerous. One, most people are familiar with carbon monoxide in their home.
Right.
From if their furnace or something else is not functioning properly, you get to lethal, perhaps
And
lethal
that's carbon
levels.
monoxide poisoning.
That's carbon monoxide poisoning. We don't see that generally in the atmosphere, fortunately. I mean, you need many parts per million of 10s to 100 parts per million of CO, carbon monoxide, to be lethal. We're looking at 100 parts per billion, so, or a few hundred parts per billion. We're well below lethal limits. However, the role that carbon monoxide plays in chemistry is very important. If carbon monoxide is oxidized by OH, the OH is not there to oxidize any other pollution.
I see.
And OH is the major scrubber, if you will, of the atmosphere. It oxidizes all other forms of pollution. So if you have a lot of carbon monoxide, you're probably going to have a lot of other pollution.
Like what?
Well, one of the things we can also measure from space is ozone.
I see.
And so ozone is not directly formed by carbon monoxide, but carbon monoxide and nitrous oxides, which primarily come from humans, combined can lead to the production of ozone in the lower atmosphere.
So this is a problem on the ground.
That's ground
so
level
this isn't
ozone.
the ozone in the stratosphere that protects us from ultraviolet light.
No, this is not the good ozone high up in the atmosphere that absorbs the sun's ultraviolet radiation, which would lessen our chance of getting skin cancer. It's ozone near the surface, where if you've ever been running outside on a day where there was a bad ozone day, you can feel it burn in your lungs. And it's oxidizing, it's doing damage to your lungs.
And this is also the threat to asthma and this sort of thing,
That's
right?
the threat to asthma as well.
Right.
And associated with that, since carbon monoxide comes from combustion, are the aerosols, the smoke, the fine particulates that come from burning of lots of things, fossil fuels, trees, that also can damage the lungs. So carbon monoxide we use as a tracer for both fire emissions and anthropogenic human pollution.
So it's a really important kind of indicator
Absolutely.
of a lot of negative processes that humans are inducing in the atmosphere, it sounds like.
Correct. It's a measure of the health of the troposphere, the lowest portion of the atmosphere.
So that's pretty important. That makes you more or less of a planet doctor.
I guess it does kind of make us
for,
look at...
for ozone.
That's right.
For carbon monoxide.
We do kind of, we do that. We look at the entire planet. We have data, we see roughly 70% of the planet every day from AIRS. There's another satellite, there's a European satellite in orbit now for the last couple of years with similar capability to AIRS called IASI, I-A-S-I, which also measures carbon monoxide as well as weather products.
So there's several different platforms. You mentioned MOPIT and AIRS. And
That's right.
These different platforms. And you work with all of these?
We work with data from all of these and have for several years. All of these are large teams of scientists.
And also from the ground?
We also do measurements from the ground. I have a ground-based instrument here at UMBC, and we use ground-based instruments at several other. The U.S. Department of Energy operates an atmospheric radiation measurement program. So there's one key ground site in kind of north central Oklahoma, out in the middle of pretty much nowhere, for the purpose of studying the conditions kind of in the central portion of the United States, far from most of the sources. And from the ground, we look at mostly the carbon monoxide that's in the lowest few kilometers, a few, 10, maybe 10,000 feet or less off the surface. From the satellite, we primarily see the region from, 10,000 feet to maybe 30,000 feet. So the combination of the two really tells us what's happening throughout the lowest portion of the atmosphere. And with both of those, we can see long-term changes. In the central United States, back from fires in 2003, there was extensive burning in Siberia. And the carbon monoxide levels that we measure at the surface in 2003 in central Oklahoma were affected by fires in Siberia.
Wow. And actually, before you were telling me that recently you've been looking at some carbon monoxide effects from fires in Los Angeles.
That's right. Most recently, we've been taking advantage of the situation, so to speak, that the huge fires that burned in Los Angeles, the station fire just north of Los Angeles in late August of this year, 2009, produced a large plume of carbon monoxide that we can see from Ayers and Yazzie and Moppet move.
All the platforms.
All the platforms
so
saw
it's
this.
very, very visible from space what's happening with the LA fires.
The LA fires were dramatically visible. It's a very large plume that we could see move from Los Angeles in about a day. It went from Los Angeles to Denver, Boulder region, Colorado. The next day it's over Oklahoma, and the next day it's over Houston.
Wow.
And what we're currently examining, we see this plume move at a region, say 5 kilometers, 15,000 feet or so off the surface. What we'd like to be able to determine is whether it impacted air quality at the surface.
So you're saying that the LA fires, as this plume of pollution basically is leaving LA, it's moving over the western United States, and it could even be coming down to the ground and causing pollution on the ground?
It could be. At least there are correlations between when the satellite saw the plume overhead and the surface measurements of both aerosols, ozone, and carbon monoxide seem to indicate that the plume did influence conditions at the surface. The detailed work that we have to do as a scientist, we have a hypothesis that this is what we see, and so we have measurements on the ground that says pollution was bad, and we have measurements from space that said we saw stuff overhead. What we have to do is a detailed analysis to put the pieces together to show that the plume overhead actually did make it down to the surface. We have previous studies where we've seen this from fires in the Pacific Northwest that impacted air quality in Houston, and we could see as the plume moved from Washington State across the central United States and then south to Texas, we could actually see the motion of the plume down towards the surface, and the ground-based measurements could see the material mix down.
Wow. It strikes me that this could be controversial, not just scientifically, but also maybe politically, as, for example, you could blame LA for your pollution if you're far away from LA.
Well, that's one of the possibilities in this, and I mean, a situation like Houston I think Houston is ranked number 4 in the country in terms both of population and general air quality, or the poorness of air quality.
Okay.
And so they're always, or quite often, especially in the summer, late August, early September, they're going to be close to exceeding the limits for pollution, for ozone. And if there's anything extra that adds to their own local pollution, then it can push them over the limit. And it's not just Houston, that can occur anywhere.
Where this occurs.
Anywhere where we see transport coming.
This will cost them money too, am I correct? The EPA will fine them for exceeding these
limits. The EPA
limits.
can fine cities and states. Generally, they withhold. What ends up is you lose highway funding if you violate some of the air quality standards.
So this is a high stakes game. If it comes down to, LA made my city's pollution exceed standards, there could almost be a litigation kind of thing involved if the science was good.
That's certainly something that could come in the future. There is an out. There's a portion of the EPA regulations that basically you can get a waiver if you can demonstrate that your exceedance was beyond your control.
I see.
Which obviously Houston has no control over the LA fires.
That's true.
LA had no control over the LA fires.
Yeah, that's a good point.
But from a climate standpoint, one of the things we're looking at is, are there certain patterns, weather patterns, that make this kind of transport more likely? And do those patterns change with time? Such as it was very hot and dry in Los Angeles when someone, unfortunately, started the fire. So the conditions were ripe for a fire there. Those same conditions also appear to have been ripe for the transport to have taken it to Houston.
I see.
So in the future, if you had a forecast of certain both conditions for fire, high fire capability, and where it's going to go, you would certainly not want to be doing any burning under those kinds of situations. As we look at long-term climate, global kind of climate change, whether humans are doing all of it or it's natural, if we can ascertain the patterns to what's happening, we can then begin to say it's going to be more likely for this to happen in the future or less likely to happen.
Well, it definitely strikes me that you've got to the point where you can answer the critic who would say, how is this relevant to people?
I hope so. I certainly think that we can say a lot of this, definitely. We can see definite impacts on things. The next step where we move in with a lot of detailed computer modeling and looking at additional data sets is to actually be able to quantify what the impacts are. It's one thing to be able to see the pictures from space and say, well, we see it move here. We really need to be able to say, and this is how much the impact is going to be, so that policymakers can make decisions. Is it a good day to burn, a good day to have certain industrial activities, or a bad day to do this, depending on what's going to be coming from somewhere else? With the satellite, we have a global view, so we can see our pollution go to Europe, we can see Europe's pollution go to Asia, and we can see Asia's pollution come to the US.
Wow, that's definitely the global view of human activity.
Yeah, it's definitely the part of the satellite gives us the really big picture.
So a while ago too, you were also talking, we spoke about methane, another trace gas in the atmosphere.
That's right.
That apparently methane had leveled off. Methane's a greenhouse gas that is one of the more important ones coming up because it's very potent per molecule.
Right.
And it apparently, all the greenhouse gases were increasing for a very long period of time. And then all of a sudden methane appeared to have stopped increasing. And now it started again.
That's
right.
right.
You were observing that from space, am I correct?
That's right. During the late 1990s, early 2000 time frame, methane, prior to that, had been increasing, leveled off. We still don't understand why it leveled off. But most recently, since about 2007, both ground-based measurements and satellite measurements show that methane is beginning to increase again in the atmosphere. And we're not exactly certain why that is. The big concern is if it's due to global change, global warming, whether it's human-induced or other, if the entire environment is warming, as the polar regions warm, as the permafrost melts, there's a vast amount of carbon, there's a vast amount of methane that's trapped in the ice. And if that is released, it could have a big impact to a negative feedback in a sense, negative in the sense of bad, but a positive feedback in the sense of, scientifically speaking, for a little bit of methane would make it warmer. Warmer means more melting, means more methane gets released, means it gets warmer. So it is a positive.
The train accelerates.
The train would accelerate greatly.
Wow,
and that's the fear, the chicken little, so to speak, that we're not quite there yet being able to say, but it certainly looks like methane is increasing.
So that we may actually be seeing acceleration of warming enhanced by this feedback effect on the Earth system.
We may be seeing the beginnings of that, and as we continue moving forward in the next several years with the satellites, we'll be able to get the global picture of whether that's continuing to happen with the confirmation from a vast network of international collaborators in Siberia, Europe, United States, Canada, people who live in the Arctic region. There are a lot of people who make measurements of methane near the surface and see those, can see those values increasing. And they can make the detailed measurements of, well, not only is methane going up, but the ground is melting. And so both of those could be very bad for humans and a lot of wildlife as well.
Yeah, it sounds like a very serious scenario. Now,
Could be.
I know for a fact also you're very involved in computation. and modeling. So tell me a little bit more about what you're doing lately with combining this observation of trace gases and their movement from space with really understanding them using models.
Well, part of what we do with the models, one of the goals as we move forward is for the satellite measurements to be able to be pulled in near real time by the models in terms for forecasting.
So it's like a weather model, similar to
like a weather
like that.
model. What the weather models do right now is there are measurements that are made from the surface, from aircraft, from weather balloons that are flown. Weather balloons are flown once or twice a day. Aircraft are flying all the time. There are lots of surface measurements. So every few hours, typically every 3 to 6 hours, the weather models are updated. You've run a forecast from previous 3 hours. You have new measurements. You bring in the new measurements to fix things where the model was maybe slightly off. And then you move forward to the next time step, so to speak. So you're always improving your computing with whatever the latest measurements are. What we're moving towards for chemical weather forecasting is doing the same thing, taking advantage of the satellite measurements as they happen. The satellite flies over. It's a roughly 90-minute orbit, so we see a different part of the planet every 90 minutes. You'd pull those measurements in near real time, and then within 3 hours to 6 hours, you'd have a new forecast with the latest satellite measurements.
Wow. So this is like the global pollution forecast?
This would be moving towards doing a global pollution forecast. There are a number of groups, several at NOAA and as well as other U.S. universities, that are doing this on an experimental basis now. As we move forward with more data and more resources from the federal government for incorporating the satellite data, that's where we'll be.
Wow.
That's the
goal.
So
theoretically, it could be just like when you go to the Weather Channel online and you see an updated map of where the rain is going to be. You could be doing something similar and saying this is where the air pollution problems are going to be.
That's right. And that's done on a more local scale now, more local to regional scale. Those forecasts are done, but they're not updated as quite in real time because they haven't had always access to that information.
So if you had access to this sort of thing, let's say it is implemented, would you yourself, would you plan your day differently like you do when you see it's probably going to rain today? Or
one certainly should move towards those kinds of things, like we already have. In Maryland, the state of Maryland does during the summer does an ozone forecast and their ozone action days where they encourage people to use mass transit on really bad forecast days. Mass transit may be made free by the policymakers. Certainly would be encouraged to reduce me driving to UMBC by myself. I would stay at home and work, perhaps, rather than necessarily driving in on the bad days. I certainly wouldn't go out and mow my yard on days or start up my charcoal grill or gas grill necessarily on days that are forecast to be bad for ozone. There are things that we could do as individuals to lessen the impact. One person's grill doesn't necessarily have a big impact, but there are lots of people who live in the Baltimore, Washington area. If everybody went out and started up their grill on the same day, could have, contribute to their poor air quality.
Interesting. It's actually pretty easy to imagine how someday your work could be applied in a framework that could be just an everyday thing.
That's certainly what we hope to have happen.
Interesting.
And that's part of what we're training our students, the next generation of scientists. That's the main roles of faculty at the university, is that I have several graduate students who are involved looking at different aspects of this. And they'll be the ones who inherit the earth that we leave. And hopefully, we'll at least be able, if we can't leave it a better place, we can at least leave them better tools to understand.
Well, very interesting stuff, Wallace. Thank you very much for
Thank you, Erle.
being interviewed here. And goodbye from the University of Maryland, Baltimore County.